may I have your attention, please? We're starting the meetup. And the slide says that we start at 19:05. We have a little bit of delay, but we're starting now. So this is the Wi-Fi password if you're not connected to Wi-Fi and you need it. So it's here on the first slide and you won't see it again. So please use the Wi-Fi now. Okay, I assume I don't see anyone typing the Wi-Fi password. So let's start. So welcome everyone to PyData Kraków number 15. Today we have the 22nd of November 2023. This is our 15th meetup. And welcome everyone. First, what is PyData? So PyData is a community of developers and users of open source data tools and educational program of known focus. And what is a known focus? And this is basically a nonprofit in the United States that serves as a fiscal sponsor for open source projects and organizing community-driven educational programs. So PyData in Kraków exists for a couple of years now, but PyData exists all over the world. There are many chapters. If you go to pydata.org, you will see all of them. And there's not just PyData meetups, but there's also PyData conferences, including online conference that happens in the next couple of days, on about 2 weeks. PyData Global, they released the schedule today. So if you go to pydata.org/global 2023, you will see what they released today. Anyway, for today, we have the two talks. The first one is going to be about exploring quantization methods for large language models by Salama. Salama is here. Then we have a networking break with pizza and beers that's sponsored by Zendesk, our host today. We're going to talk about it more in a minute. Then we have another talk by Dr. Maciej Majewski, who's over there. And then we have lightning talks. Lightning talks are, well, let's go through talks first. So the exploring the quantization methods for large language models. Then we have the taming the few-shot learning. And the lightning talks. If you want to talk about any topic 4 or 5 minutes, we can talk about it after the talks. We'll have basically like an open mic session for lightning talks. If you want to talk about something, please talk to us during the break and we will set it up. Now, who's the sponsors of today's event? We have Zendesk, and we have somebody from Zendesk who will tell us more about our host today.
Good evening, PyData. Welcome to Zendesk. It's really great honor and pleasure to have you here in our offices today. My name is Tomek Krzyżak. I'm the VP of Software Engineering and the site lead for Zendesk in Poland. I just wanted to tell you a little bit about Zendesk. I'm not sure if you know who we are, what we do. Literally 5-10 minutes of the introduction. So who we are undisputable leader, disruptor, and innovator in customer experience. Customer experience is the domain which essentially touches all the points when customer has interaction with essentially services from our customers. And we are supporting many of them. One of the things which I wanted to also let you know that we are really big and global company. We have roughly 150,000 of customers from all around the world. We have $1.7 billion revenue, annual actually recurring revenue. We employ over 5,000 employees globally in our company. In addition to that, vast majority of the business essentially comes from, not vast majority, 50% comes from America and 50% from the rest of the world. We have headquarters in San Francisco, in California. We have 15 offices around the globe, so essentially in every continent we have presence. Who do we support? We are supporting all actually big logos from around the world. And you can see that we are touching every vertical, starting with retail, manufacturing, through healthcare technology, finishing up with media and entertainment, as well as some educational institutions and others. In terms of Zendesk in Poland, our history goes back to 2008. 2009, when there was a startup in Kraków, very successful, called Base. I don't know if you are aware of it, but it was very, very successful startup, not only in terms of Kraków, but in general in Poland. Base was acquired by Zendesk in 2018, so it was exactly 5 years ago, and this is when actually our presence starts in Kraków and in Poland. And just a couple of weeks ago, we've celebrated our 5th anniversary here. We had really nice party actually in our offices. We had several guests from outside and from inside of our company. And I think that you've already noticed we have really nice and beautiful office, which was designed to essentially serve our way of working, a lot of collaboration spaces, really quiet areas where we can focus on the work. We employ currently 200 employees, roughly, slightly over. We have very successful internship program. We have over 20 interns actually from around Poland. And we are developing and supporting critical products for Zendesk. That includes Cell, which is the former Base product, Explore, as well as TimeShift, which is workforce management tool. And at the very end, well, I mean, last but not least, we are also focusing on machine learning and artificial intelligence, which is tightly connected with the topic of this meetup today. And by the way, we are hiring. So if you will be interested in looking at our jobs page, I really encourage you to do so. So thank you so much. I hope that you will enjoy the rest of the evening. Drinks and food. Food will be actually later there in the kitchen. Drinks are already there. So thank you so much, and the floor is yours. Thank you.
Thank you, Zendesk, for hosting us today. And now for more sponsors, we also have Kluk, who's doing the streaming today. This event is the first PyData, I think, that we had in Kraków that is live streamed and recorded. So a round of applause for Kluk, please. Now, if you'd like to sponsor one of our future events, you can send us an email or talk to us during the break. And yeah, we also have a Discord server. If you go to PyData.krk.pl or discord.pydata.krk.pl, there's an invite. There's also the QR code that you can scan. And the Discord is particularly active in December because we're doing the Advent of Code there. So we will talk, I think Maciej will talk about it a little bit more later on. Next event, we don't have a date yet, but we're always looking for speakers. So if you'd like to speak on one of the PyData events in the future, let us know either on Discord or send us an email or talk to us during the break. And we're aiming for one event every 2 months or so. And thank you, Zendesk, again. And now on to the first presentation, which is Exploring Quantization Methods for Large Language Models by Salama.
And we're gonna talk about making LLMs smaller. So yeah, when we approach the machine learning models, they usually tend to grow and grow and grow. It was already with GPT-2 when it was really huge. With the current llamas and other models, we tend to not fit them on our laptops, even if they are really cool and good. So to go quickly through the neural networks, because I'm not sure how many of us are fully aware what we are going to talk about, we have the weights, we have the inputs, and once you multiply them, do the summation, do the bias addition, and move it through the activation function, we have the simplest logistic regression or neural network, however you want to call it. But to make it smaller, you have to go really deep down to the hardware. And you have to think of how our weights are written down and calculated. So here we have the signed integer number. The first bit one that you see on the left side is the bit that is corresponding to the negative or positive number. And then the following weights are just the consequential exponents of number 2, which give us representation from 2 to n to the power of n minus 1, usually. Okay. Then we're getting into the into fixed point numbers when we want to have some fractions. So the idea is still the same. We have the first bit corresponding to the, whether it's a negative or positive number, then the green part would correspond to the integer part, and then for the fraction. And here is the case. So usually when we calculate in our neural networks, we really tend to think that those fractions have a lot to say. And we have some standards that were introduced way back before, like IEEE with the 32-bit float, single precision, the most common on any computer science course. This is in Python, the float. Then we have the half precision, which is more commonly used within the machine learning, as we don't really tend to care that much, or we actually don't have we need more computation power to calculate this. And then we have the Google Brain float, which even decreased the number of precision float for the half precision. So you see this tendency to decrease and remove the floating point, and whole point of making those LLMs able to like refine them or pre-tune them or doing the inference is to basically remove the floating points. Okay, so how are we gonna then adjust the integer part on this? So you could think of the quantization as like basically changing the numbers of pixels in the picture that represents for actually the color plate, and the more you decrease it, you can still recognize a lot of the features, but you don't spend too much of a computation there. And mathematically, when you have a signal, you can make it discrete, and then you have these quantization errors that appear, and we try to basically somehow fight with them to make our models still work pretty fine. And the simplest way is to basically do the round to the nearest. So basically, we just putting the round function over our float number, and then we get in some kind of integers, but how much they really correspond to our weights and how our network gonna work afterwards is not so obvious. And as you can imagine, it's not the best way to quantize our models. We have few groups which have the pros and cons, and three most commonly used as for now quantization methods. Of course, we have different types that build on top of them. I'm gonna speak at least about one of them. And yeah, so we usually care about the storage and computation. So the storage is really expensive, and moving the data on the processors, it's expensive, and it's usually more expensive than just the pure computation. So we have the k-means based quantization, linear quantization, and binary quantization. We're not going to talk about the binary one, although it really cool and interesting, but we don't have time for that one. We're going to talk a little bit about k-means based quantization to have some basic understanding about the quantization as a whole, and the linear quantization, which is commonly used within our favorite libraries like PyTorch or TensorFlow. Yeah, let's get to the k-means based weight quantization. So yeah, let's focus on the matrix weight on the left. So each number is represented by 32-bit floats, and we want to cluster those numbers. So instead of doing just purely round on top of it, we want to do the k-means clustering on it, and then assign the clusters for the corresponding numbers, and have this code book that will basically be the help for us to read back the weights. And by this one, we can basically scale, or actually scale down the weights by at least 3.2 times. But the less bit we use, this is usually the scale, so 32 by n, smaller one. And here we have the quantization error once we reconstruct one. So basically, reconstruction is just the inserting those numbers here and just doing the subtraction. And here are some charts with basic results. It's on the AlexNet, on the ImageNet dataset. I'm not sure how much. Okay, the pruning one, the pruning word. So the pruning is even more tough than the quantization. Pruning is actually removing the weights, putting them into the zeros, and usually most of the weights are just useless, or they don't give much of a value. And we can basically firstly remove the weights, some of them, and then do the quantization to even downgrade the model. So as you see here, for the, let's say, 3.5% of the original number of size of the ratio, when we basically combine the pruning and quantization, have very low accuracy loss, which is very cool for us engineers, because we're saving the inferencing time, basically speeding up. We don't have to have so much RAM, so we can run it sometimes on our local computers. And thirdly, if somebody cares, it's less of an energy that our processor is spending. So time is usually the money, and that's why we care so much about this. Here is the framework that was introduced by the. Okay, so basically, whole presentation is like basically merging a few of the presentations or lectures done by MIT Han Lab, which I really advise everyone to go into if anyone is interested into it. And they want to basically run models like Llama 2 on the edge devices, like your smartphone or even the smaller devices, and they successfully doing it. So they have this deep compression framework where they firstly pruning the model, then doing the quantization, and then some sort of encoding. And here are the results. So basically, they are able to scale down by, for example, for the GoogleNet by 10, for the VGGNet by 49. But what is more interesting, sometimes they're getting better accuracy than the original model. Especially for the test sets, because then we have more generalized model. Then we heading to the linear quantization, which is much harder. We want to represent our numbers, the real numbers, as this equation. Okay, Q is given. This is the quantized weights. And S and Z, we have to figure it out and find them. And here is the differences between the libraries that are implementing those models. Okay, one of them. Okay, so what is the way to basically find the S and Z parameters? We take in the range of the weights that we have within our matrix, and then scale it down to the bits, actually the maximum numbers that we have for the current bits. So if you have 4 bits, then the maximum is number something. I don't remember, but yeah, -8 to 7. This is the range, and basically want to scale it down. And this is what the affine mapping means in mathematics. So in mathematics, affine transformation is such that the distance within the set is preserved, and this is what we want to do. Not getting much into the mathematics behind it, we can end up to rescale to the n-bit integer multiplication for only those 3 parameters within our network. And yeah, so getting out from the float 32 into n-bit, as you will see soon, is kind of very interesting. The same can be applied for the convolution networks. And yeah, and here is the calculation of it. So the S parameter, we just basically scale it down. So we take the maximum range, subtract from it the minimum one, and divide it by the range of the maximum values of the bits that we can have. Based on that, we can recalculate the z, and z is kind of our 0 within the new set. And this is the most tricky part. So most of the libraries that you're going to use for quantization will have this parameter z, what is our 0. And yeah, PyTorch, for example, is using this type of quantization. But the TensorFlow, for example, in TensorFlow, we are able to basically, they're using z as a 0 point within the set. It sometimes requires the shifting of the numbers anyway, but it's simplifying our calculations by far. And here is the results again. Scaling down from the floating point into 8-bit integer quantization, you can see that we have very, very small loss of the accuracy, while latency can increase highly, like from example, from 70 milliseconds to 120. It's kind of a lot, and especially as you see in here, it's run on the Snapdragon, means smartphone. But within the LLM, it's not so fun. It's not so easy as with the convolution neural networks. It requires a little bit more of carefulness. How we, it's not just simply apply this method and it's going to work. Have to do some tricks here. So here are some of the most common methods like GGUF, previously named by GGML, BNB and F4, AWQ and GPTQ. And yeah, and they differ. So some of them require the data dependencies, dependence. Some of them no. Only one of them listed here, you are able to basically run on the fly. So before you load it into your graphical card, you can quantize it. And they differ with the speed. So the faster one for the CPU is GGUF. And you have one library written in C++ that is doing the job. And the other one that we're going to talk about more a little bit today is AWQ. Yep. So AWQ, activation aware weight quantization for LLM compression and acceleration. What does it mean? Again, we have the round to nearest, so we can try to just round the numbers here and get some weights and call them quantized numbers or weights. But then, as you see in perplexity, which is the measurement of how well you predict the next word, is degrading highly. I mean, the lower perplexity, the better. So we can improve them by grouping the weights before we scale them out, but it's not given that much of the improvements. Here is the grouping. What does it mean? Maybe we don't have to get into it right now. Yeah. So the HandLab, I'm not sure if it was them actually, but basically we can just keep only 0.1% of the important weights within the channel, and these can, as a full precision of 16 floating point 16 half precision floating numbers, and these improve immensely the perplexity. But then getting into problems with the mixed precision on the quantized matrix, and this makes a problem for our kernels usually. So how do we select the silent channels? That's the first thing, and how to remove these floating points here and keep this accuracy for our LLMs. So the idea is, first one is to look at the weights. This is especially common with the pruning, and that we're just looking for the big weights in certain channels, or the distribution that is big, and we try to keep them. And here we have the result. So the improvement is there, but it's smaller, really small. But the other idea is to look at the activations. So look at the output of the activation function and look at the distribution there. So these give us a much bigger improvement. And as you can see, looking at only on the weights, it's just not much of a difference than taking the random channel and leave it as a full precision. Okay, so we know the answer. The answer is look at the activation distribution and choose the biggest distribution there. But how to remove the floating point? And here is the trick. The trick is the following. So on the knowing the channel that will be for the output from the activation input output, we're gonna be knowing that which of the row actually, which channel in the weights we have to focus on. And the trick is to scale it up, bigger than 1. So we scale it, and magically we're getting back to the really good perplexity. And how does it work? So normally, if we just have the linear layer here, so we have the weights and we have the inputs that we want to weight against. We will have to scale it by some factor, and then rescale the weights back. So the idea is to scale the weights and downgrade the x, the input, into our linear layer. And without the quantization, it's of course the same. It's just 1. But with putting the quantization on top of the scaling of the weights, we're getting some errors. So how to choose this number s to scale it properly? The idea is to take the weights and take the range of it and divide it by the number, the biggest value of the quantization that we taken of the bits. And here is the case. So this means taking the centroids and taking the distance between the particular centroids. Then we're taking the round function on top of the weights, divided by this distance, multiplied by distance, and this is our quantization method. If we scale it, if we scale it, this delta that we have here is almost always the same. The round function will change, but the average of the error is just 2.5. Basically, we can, if we round the 1.5 to it's 2. If we round 1.7, it's also 2. So the maximum error that we can have on average is 0.25. And the parameter here, s, is the one that is basically scaling down this error. So the bigger the S, at least bigger than 1, the better accuracy we get in. Yeah. And those are the results as I showed before. So by scaling down, they found that the parameter 2 is really good, but not always. And to find it on the fly, the AWQ is taking your data, running it through the network, checking the activations, and doing the fast grid search on certain range of the values S and finding the best value. That's why you need to run it through the data, and this is the tricky point, because in the paper itself it was written that it shouldn't matter because LLMs are so huge and they usually models that tend to generalize and being good at the generalization part, but not always. So if you fine tune your model, perhaps it's better to run it through your own data, not just downloading it from the internet and hoping that it's gonna be fine. Here is the here are the results of the perplexity comparing to GPTQ, and that was previously one of the best models methods to quantization. And yeah, they tend to hold this low perplexity for throughout the different models of Llama. Yeah, and this model also works fine for the multimodal LLMs. So like the Open Flamingo, where we want to have the picture and we want to put a description out there. So here you have the naive like rounding method, where we're just rounding the weights, and here you have the AWQ that basically finding that 2 toy airplanes sit on a grass field, which is correct. And the previous one said that a model airplane flying in the sky. The same goes with the other pictures. Performance. Since we're downgrading the number of bits that we need for the multiplication of our matrix for the weights, we're getting higher performance. And that's really important because usually as you're running, for example, your GPT-4, it's kind of slow, yeah? So with the quantization, you could improve highly the performance of it. As you see in the AWQ run on the 4 bits weights and keeping the activations on the precision of 16 floating points on the 16 bits, it's way better than Hugging Face baseline. Okay, noise. And here is the credits and more info that if you want to look for the quantization methods or pruning or trying to run your models on the edge devices, I highly recommend the MIT HandLab, but also Trails Research. And not thank you fully, because we have also, I would like you to see how simple it is. So we have few libraries here. The authors of the paper of AWQ, they have their own library, but we have the one that is commonly used within the internet is AutoAWQ. And it's as simple as just pipe install AutoAWQ, import the following package, and yeah, and firstly we loading the models. We need the weights. Secondly, we need the tokenizer, as we usually do when we try to run our model, and then just model quantize. Simple as that. But we have to give the calibration data. As I mentioned, this is the tricky point, because yes, we can try to trust that it's always good for any type of a data, but maybe if you want to improve it on your old data would be much, or at least with the data that have similar distribution that your data set, it could be way better. Yeah, then you just save the quantized model and here we go, you can run it. It's so simple. So yeah, that's it. If there are any questions, I'm here to answer them. the question, yeah? Go ahead. Cool.
So this piece of code that you have been showing us at the end, this is runnable on the laptop, right?
Okay, so it depends on the model that you load in. Like Llama 7B, it's usually like 14 gigabytes, and you can downgrade with the AWQ to 3.54 gigabytes of your model.
And in
So
the worst case, with the biggest model, then
70B, yeah.
Okay.
Yeah, it's kind of a lot. So you can calculate it, but it's way more. But the idea is basically to even if you don't have it, if you cannot run it or quantize it on your laptop, at least try to run it somewhere like in the Google Cloud or wherever, and then try to download it and try to do the fine tuning on your laptop if you wish.
Okay. Just maybe another question. Have you tried this sort of stuff with vision transformers?
I haven't.
Do you know if it works or?
Okay, so for the multimodal, they say that it works fine itself.
Okay.
Yeah.
Right.
Yeah.
Okay. Thank you.
Okay, the second question, the Ablef, yeah.
Yeah, so forgive my ignorance, but can you tell me where the fine-tuning fits in the whole picture here? So do I quantize the model only for the inference, or can I quantize the model and fine-tune the model and have easier time to fine-tune because I have, less numbers to crunch?
Okay, so they're trying right now to put it everywhere, including training. So there's like quantized training even. And yeah, we have for the fine tuning, we have like the LoRa method that is commonly used right now, and you have the QLoRa, the quantized version of it. So yeah, there is a quantized version of it. But which quantization method is used, I'm not sure. I haven't checked it. Usually it's the linear quantization. It's
Okay,
yeah,
thanks.
the best accuracy.
How is it possible that a quantized model has better accuracy sometimes than
So if we have overfitted model on our data, yeah, sometimes we just downgrading the accuracy, and yeah, it's just better on the test set. Okay.
So now we'll start a short break, and there is food and drinks over there in the kitchen. And see you back here in about 20, 30 minutes, something like that. Okay. Najpierw robimy reklamę Pythonika, a potem robimy... Okay. Welcome back, everyone, after the short break. I hope you enjoyed the pizza, and thank you again, Zendesk, for hosting us and for providing us with the pizza and with the drinks. We're going to be slowly restarting and then coming to the other talk of the day, but before we have a short announcement about a different meetup that's happening next week, and Nico will tell us about the next meetup.
Hey, nice to see you all. My name is Marcin, some of you may know me as Nico, and I want to invite you to the PyConic. It will be next week. More information you can find on the website. It's Thursday, 6:30. More information also you can find on the meetup website. And there will be main talk. Main talk will be about Django and the Fast API. And I will be talking about Python and Rust integration. And after that, we expect that there will be performance nirvana. You can visit also my GitHub page. There is a secret hidden there. Everyone who will find it can provide the password next week, and we'll have some small gift for you. And that's all. So if you are still hungry, next week will be pizza as well, I think. Thank you.
Thank you, Nico, and hopefully see you all next week at PyConic at Agiha. If you go to the PyConic website, pyconic.org, or meetup.com/PyConic, you will find all the details there. Now we're going to start with our second talk of the day, which is going to be by Dr. Maciej Majewski, and it's going to be about few-shot learning. So take it away, Maciej, and a round of applause for Maciej.
So, as Artur said, my name is Maciej Majewski, and today I will be talking about the few-shot learning. So, who am I? I am currently working as an image recognition team leader at Omnias, which is a startup. And I also graduated with master in computer science at AGH and PhD in particle physics at AGH/CERN. I have some experience with Python. My main focus or area that I'm interested in about machine learning is computer vision. Also, I'm conducting a course at AGH called Python in the Enterprise. And here you can see also my hobbies, and I really like going to the mountains. So let's talk about this topic. So the goal of this talk is to let you know what few-shot learning is, to explain vectorization and metric learning, show some possible architectures that solve problems of few-shot learning, how it is used, and at the end there will be some introduction to the state-of-the-art solution for few-shot learning. And also there will be some bold claims that will hopefully spark some conversations later at the possible after party. Yeah, so I will be talking about why do we need few-shot learning. Before, I will tell you what it is. And then I will talk about types of few-shot learning, as I said, vectorization, metric learning, and some problems of the few-shot learning. Okay, so how it generally works in machine learning. We have our model, a network, that usually gives us some output. In the case of the classification tasks, the output can be 0 or 1 if it's like binary classification, or it can be one-hot encoded, and it can be or of any length pretty much. And the length of the output in the one-hot encoding is the amount of classes as well. Yeah, this works great, but it has some flaws. Like in order to be able to recognize something with this approach, we need a lot of a huge data set mostly. Training can take a long time. And if we would like to add some new classes to be recognized with our model, then, well, we pretty much need to change our architecture because, well, we need to add another class to the output. And that can be covered in many different ways, but it's troublesome. Also, we need to balance the data set so that each class would be approximately of the same size. So let's take this approach and very naively try to use it in the problem of face recognition, right? We have 8 billion people at our planet, and usually the photos, the reference photos of a person are few, just a few images. And if we would apply that naively, we would need some model that has the output length of 8 billion, which is not great. And also we would have to get a face of pretty much everyone on the Earth to be able to distinguish people between each other, which is not really feasible, right? So this is where the few-shot learning comes in. There are multiple different types of tasks for few-shot learning. Generally, like the language around here is not very consistent. It's not certain, and some people use it in some way, some people are using it in other way. But generally, few-shot learning, we can sort of split recursively at first, because we have few-shot learning, one-shot learning, and zero-shot learning. So generally about few-shot learning, we can say this. Usually when we talk about few-shot learning, we mean something in terms of n-way k-shot learning. That sounds cryptic, and I think it's not the best way of putting it. But what we really mean here is n-way k-shot means number of classes and number of samples. So 5-way 2-shot learning is 5 classes to recognize and 2 examples in each of the class. And this set we call support set, which is sort of a training set. And we also have query set, which are images that we don't know what the classes are. And this is how it usually works. So we have n-way k-shot. So what's the difference? Now it's easy, because few-shot learning is n-way k-shot learning, one-shot learning is n-way one-shot learning, and zero-shot learning is n-way zero-shot learning. So it's just the matter of number of samples in the class, nothing more. usually, mostly. Zero-shot learning in this sense is kind of different than the other cases because zero means here that we have no classes here to recognize, and it's sort of true because we can sort of describe it using this this model with joint text and images. So if we train a model using descriptions of the images along with images, then this model might have a possibility to know what a tiger is only given description, right? So it can understand something that is between all of those. You show it what a cat is, what a lion is, what horse is, and we hope that it will understand more or less what a tiger is. Okay, so how do we solve this problem? Conceptually, those kind of problems with few-shot learning, if we have a low number of samples and some classes, we can always try to approach with this naive classical approach. But one of the most popular approaches is using vectorization and metric spaces. What are those? So vectorization means pretty much taking something and making it a vector. You can take image, you can take sound, you can take video, you can take some piece of text and make vector out of it. And in a sense of like really simple float vector. How it can be done? We can take a very basic model architecture and we can, for example, here cut it at some later layer and we can get output of this cutted layer and we can flatten it out straight if it's matrix or some weird shape and say, okay, this is our vector. And this vector is also what is sometimes referred to as embedding. So that works pretty much interchangeably. Okay, but why is it useful to make vectors? Because if we have vectors, we can calculate difference between them. Actually, there are many different ways of calculating difference and similarity. And here, if you will see, we have an example of a cut input of image x1 that is passed to a network and it creates a vector v1. And here we have a dog x2 and it also creates a vector v2. And if we will vectorize those for images, we can calculate distances or differences. And in the case where the samples are coming from different classes, then the distance should be maximally big, right? And in the case if it's in the same classes, the examples come from the same class, the distance should be minimal. And we can use a pre-trained network to get those vectors. And as I said, there are many different ways to calculate a similarity between vectors. For example, even we can treat a string as a vector and count number of substitutions. There is Euclidean distance, cosine similarity, dot product, many different ways to do that. Okay, so if we take this model and we'll cut the latter parts, and we'll take the output of whatever we put in this model, it doesn't guarantee, there's no guarantee that the output will actually give us such nice metric, that the similar things from the same class will be not so distant, given some metric distance, to each other. In other words, what if the distance in the space created by the model does not reflect similarity of the objects? We can work with a model to actually prepare it for exactly that. One of the ways is using triplet loss. Triplet loss is, as the name suggests, a loss that is calculated between pretty much three things. In triplet loss, we have 3 objects, anchor, positive, and negative. And here in the example with the images, we have anchor image, positive image, and negative image. And anchor is here works sort of as a ground truth because it's the class that we want to use for optimization. It's this example, sorry, not class. And we calculate embeddings for each of those. And we want for the anchor to be as close to the positive case and as farther from the negative case in our created metric space, in this vector space that the model creates. So it could be, for example, a 3D space, why not? So in that sense, it could be really a distance how we understand it in a 3D space. And we use loss like this to do that. So what we are actually doing here, we are calculating the distance between the feature vector, between the vector that comes from the anchor example and the positive example. This is positive value, should be positive value, and this is a negative value, and this is about the negative example. So something that comes from the much different class. And we add those things together. We have here a minus sign, and this is some margin value that we don't care about right now. And this is how it works. So the desire here for this loss is that the examples of the same class would be grouped as closely together as possible. But at the same time, examples of different classes, like those, we can call them clusters even, should be as farther apart as possible. And actually, this is not the only metric that we can use in metric learning. There are multiple different metrics. That was just one example how we can do it. Okay, now you know what is a few shot learning, that we can formalize it in terms of number of classes and case shots, which means samples, and that we have support set, which is a training set, pretty much, and query set that is actually containing images that we don't know. And you know what is vectorization? We simply take some image in case of image tasks and create vector out of it. And you also know what is metric learning. So the goal is here to have for this vector space to create a space where cases from the same classes are close to each other and cases from different classes are farther apart. Okay, and here is putting it all together. So what we have here is support set with some images and a query set that we have here with also some images of the birds. And the question here is pretty much to match which part of those images is fitting which class. So what we do is, as I said, first we vectorize stuff. How to do it? We can take some pre-trained model. We can assume that it was trained in such manner that the metric space is working well there. And we then take those vectors calculated and we use similarity function. It can be as simple as calculating distance to each of those images between each other. So we calculate distance between this image, this unknown image, and this image, and this image, and this image, and we do so for the whole set. And we pick the image that is the closest to this one coming from the query. And we know what this image is class of, so we can assign to this image this class. That's one of the ways that you can do it. Okay, so that is actually quite important here. I hope that everyone sort of understood what I was saying. I would appreciate if you would nod. Yes, okay, great. Great. Okay. Yes, so that's cool, but why am I doing this talk? Well, once you sort of get into this field and start seeing it, you will start seeing it everywhere pretty much. And I mean everywhere. So one more thing, vectorization. As I said, the language here is not very precise. Sometimes people mean few-shot learning and vectorizations, they use them at the same time. I would prefer to use vectorization because it's sort of better term that is not closing the application of this method towards only few-shot cases. And with vectorization, we can do much more than only calculate similarity. Yeah, one example of that you see it everywhere. This is an actual paper for GPT-3, which says language models are few-shot learners. Well, I think that few-shot learning done this way is kind of a future in machine learning. Although it requires huge data set anyway, not exactly of the thing that you are trying to, let's say, classify, and proven method for unsupervised training. So if your data set that you would like to apply vectorization or few-shot learning on is not big enough or has proven method for unsupervised training, it may not work easily. Once again, pretty much the same stuff. How how this library LangChain, how many of you have heard about LangChain? Raise your hand. Yeah, some people. Great, great. So it's pretty much how it works. Exactly the same stuff. So let's take a text or a repository or some kind of document or a documentation for some device or something, or I don't know, whatever you like, whatever kind of a text you like. Let's say that we take the Hitchhiker's Guide to the Galaxy, right? We can then we could chunk it into pieces to limit sort of the sizes of the vectors, how much data is fitting the vectors. Let's say 1,000 words each. And at those chunks, we vectorize. We vectorize those chunks and we store it in, I don't know, some kind of database. Then we create a query. What is the answer to life? And this query, we also can vectorize, right? Language models are allowing this sort of stuff. And well, if we have those things vectorized, we can calculate similarity score between each of those. Why we should do that? Because when we have a vector of a question, we assume that the vectors of the relevant pieces of text will be close to each other, which makes sense, right? If you are trying to answer some question, then you would be looking for relevant pieces of text in whatever base text you have. Then, using that, we select, let's say, a few vectors that are relevant to the query. And in LangChain, and I did it myself, and I went inside the code and actually looked for it, it really works like this, that they were at some point, at least, were doing stuff like this. They had a piece of string that said, "Dear Chad, given this context," and then you paste in the stuff that comes from the similarity scoring, and then they add a little bit more string, answer this question, and then you paste the question. And now this whole machine is able to answer the question with the context. What is also nice is that you don't have to do a lot of requests for vectorization here, because you are calculating the similarity scoring. You don't need to put everything here all the time. You just need to put stuff that is relevant. Well, that's exactly few-shot learning, right? We have support set, which is a set of knowledge that comes from some text, some documentation, whatever. And we have query set, which is a question, which is query, which is exactly what it is. And what we do is we calculate similarity score, and then we have our answer. The stuff here is sort of different, because usually in few-shot learning, we just care about something that is most similar. But here, we just use it to feed it again. Yeah, so really, the paper title was true. GPT is a few-shot learner. And this is basically what, at least last when I checked a few months ago, this is what happened to the natural language processing mostly. So there have come out a lot of stuff, a lot of databases that are actually covering the part that is actually storing the vectors and doing the search, which is a nice way, because there are a lot of optimizations that can be done there in terms of searching. Because if you have a lot of vectors, then it also becomes a problem, because you need to calculate the similarity score between all of those, in theory, right? So there are some optimizations that can be done. Okay, how about computer vision? Well, that's pretty much how you implement the reverse image search, right? There is a database of the images that you vectorized, and then you do nearest neighbor search here, and then you get rankings of what is most similar to that given image. Yeah, okay. So this is the part that I wanted to talk about, the state-of-the-art solution for one of the few-shot learning problems when it comes to image classification. So you can see here the accuracy during the years. This is taken from papers with code, and how it's growing. And you can see that this is 90%. It's not exactly what you will see in later slides, because, well, usually when people are doing papers on this sort of stuff, it's not only in one data set, and this graph is showing only results for one data set. But you can see how much did it grow from 2016, when we had like 60% or something, to almost 90% here. This paper that I wanted to talk about is called Pushing the Limits of Simple Pipelines for Few-Shot Learning, External Data and Fine-Tuning Make a Difference. Which is exactly that. Guys that were doing this paper actually didn't pretty much do anything novel. They just took some stuff that was already there, refined it a little bit, and put it out. It's using visual transformers. So if you don't know what visual transformer is, you will have to think about transformer very hard and think about vision, and that's pretty much it. They use something called Dino, which is self-supervised method of learning, and prototypical networks, which is kind of a gimmick that you can use with metric spaces. Dino. It's not it. It's BIOL. Dino is a version of a thing called BIOL, which stands for Bootstrap Your Own Latent. And Dino stands for Distillation with No Labels. It's a self-supervised technique that takes an input image, actually takes a crop out of it, and actually does 2 crops, and is showing it to the network. And those crops are also slightly modified, so they would be a little bit different. And it's passing it through networks. Actually, it's kind of at the same network. This network, called target network, is creating a target to aim at for the other one that will be optimized for So the online network will be optimized for whatever the target network will show in the end. And why does it work from 0 to ground up? Because of this exponential moving average. What you need to understand here is that this is a technique that allows for gradually moving the weights from online network to target network. And this way, those two things are learning sort of each other. This is a student-teacher situation. And this is actually how BEOL works. And Dino is a little bit built on top of that. What is nice here, in this case, you don't need labeled images. You don't. You can use unlabeled stuff. Prototypical networks. This is sort of a method of optimization, kind of like the triplet loss, but with a little twist how it's calculated. Every time, with every pass of a batch, I think it was, we are calculating, of course, the vectors and their position in the space, and also we are calculating centroids. Centroids here are marked by those dark dots. And this loss is combining the distance of each of the cases here to the centroid with the distance between the centroids to each other. And this is kind of a variation on a triplet loss. Okay, and this is a very kind of confusing graph from the authors of this paper. But what they meant here is that this the workflow that they are proposing is consisting of multiple steps and multiple refinements over the same stuff. So first we have pre-trained backbone, which is actually the part that is Dino stuff BEOL is going on. So we have some pre-trained network, and we are also training it using some general data sets with this prototypical networks. We are training using some domain data, because this model was created for multiple different domains, and in some cases the domains of the task were not really overlapping. They added this next step that is actually training the model on the support set itself. So on the sort of a training set that we are actually doing comparisons to, but they said that using just a few steps coming from the support data set really helps this architecture. Well, and here are the results of this method. And as you can see, it works quite really well. They also used this approach with ResNet as well as visual transformers, so Dino. And there is one metric that they didn't had like the best result, although they had quite good results anyway. But what is annoying to me is that that it is still 5-way one-shot learning and 5-way 5-shot learning, and only that. It's not like thousands of classes, which I would like to have, because that would be very nice for computer vision to really have this sort of precision of recognition. That's only 5 classes. And in the case of GPT, for example, we are, well, generalizing over a lot of stuff with not a lot of samples, right? So the question for the conversation is, when will we have many-way few-shot learning models for computer vision, when the n is equal to thousands or 10,000, and the shot will be equal to 1, for example. Okay, so summary. Few-shot learning is way more present than you may think. It allows to find solution to the problems that require really small amounts of data. The vectorization and similarity scoring, I think, is way of solving ML problems without training. Remember that those models that we used for vectorizations they don't often need any training on the data set that you would like to use. In my opinion, the vectorization is the way of the future. And that's it for today. Thank you. Do you have any questions? I have one question.
Thank you. Hello. Thank you for the presentation. For the last sentence, you said that normally we don't need to train like we have this base model that we're using for the vectorization. Did I understand well that normally we don't need it? We don't need to train the model on the support data, but
Yes.
the last paper you said that we can get some better results when we fine-tune this, let's say, base model.
Yes. So the matter here is a little bit more complicated because in some cases, no one will disallow you to have the support set used for training, right? But in cases like when your support set is so small that you actually, there is no point of putting it to the training, you don't need to put it to the training. In the case of this paper that I have shown, they were actually doing stuff like training, for example, on the not only for the vision, not only for the image, but for text as well. So, for example, if it would be text in English, right, and the support set would be in, I don't know, French, they suggested that a few steps, small steps from the support set actually is helping towards this recognition. But usually support set is created for doing the checks between the vectors.
Okay, thank you. So I guess that it will be the same for the vision. So if we take a model, the base model that was trained on, I don't know, some images, and then we have our support set, which is completely different.
Yes.
It would be better to
yes. For example, if you would have trained something on ImageNet data set with like animals and stuff, and your data set is actually, I don't know, X-rays of lung, right? Then it makes sense to train it. Pretty much, it's better to train your model anyway on the data that you have. But sometimes, I don't know, you may not have enough time or enough resources, or you have not enough even cases that it makes sense.
Okay, last question. In the context of GPT, so in the language models, how do you, when you showed this example that we put some textbook inside, we ask the question, how do you make it that when you ask a question, the model will answer actually on the question, and it will not just output what will follow the question in the original book, like the narratives, like what is the answer to life? Asked John.
Yeah. So how do you do that? You just politely ask here, answer this question, and hope that it will not be doing exactly that, because this is the part of now solving problems with LangChain and GPT specifically, is that, well, that you don't have control over GPT. You can politely ask it to do a thing, and well, actually, in this slide, it kind of shows you what actually the prompt engineering is, right? It's crafting a vector that is precisely the way that you want it. It's like trying to map your mind to this vector, right? That will be fitted well inside the GPT.
Thank you.
Yeah.
So can you confirm, did I get it right? You have a support set and you can use it as a training set to fine-tune the model, and then you can basically vectorize all the instances from the support set and do kind of a k nearest neighbors between the support set and the query.
Yeah.
Cool.
Yeah,
Thanks.
I mean, in the field, I think the requirement is that you generally don't do that because it's in a bad taste, because it's not really then like using this proper way of doing few shot learning. But really, if you are working on something that you need it to work, well, you can just train it, right? No one will say that it's bad. It's slightly easier case when you are training with the use of support set, because the metric space that you are creating with your model is actually better reflecting the cases that are inside the support set, right? So it's actually usually should have better accuracy there.
So a follow-up question, what's the point then to train or like have a separate training set for the fine-tuning and then using a support set, if you can just use a support set for the training?
Yeah. So here they sort of separated those things because it's a paper, right? And they want to have a proper few shot learning. So not actually proper few shot learning, but here they want to do use support set that is not contained within the training, right? Because that's actually the way that you, I think at least, that's the way that you work with those benchmarks.
Okay, gotcha. So just the last one. Have you tried this method on quantized models?
No, I did not.
Okay.
But
Thanks.
it's it's curious how it would work together. Yeah.
Hey, I've got a question that's related to your LangChain example, because that's sort of essentially like I do similar stuff at work with my team, and it's around like similarity scoring. Do you have any like recommendations for optimizing the similarity threshold? Because I suppose sort of what we do right now is that we've got a set of questions that we would ask to the model, and we look at the answers that we get back, and it's I guess one of the ways that we would see if the score is like high or low enough. But it's sort of like a trial and error approach, and we haven't really found any alternative approaches to set the similarity score.
What I would do in this case, it depends, of course, what kind of task
Yeah.
you have there. But I would take a look at the distribution of this similarity score. Right, to see like a histogram, a graph, and then see, okay, most of the cases are here or there, and we can limit it by cutting at this step. But generally speaking, for NLP and GPT, it might be, I assume it might be difficult, and also those things have some of that stuff built in.
Yep. Yeah.
As far as I know.
Okay, thanks.
Just a quick comment about the similarity scores. We actually did quite similar experiments, and actually segmenting data with the proper sizes can help, because the similar scores are usually are more for semantic similarities, right? So the if you have too much data, and the vectors can be calculated in a very similar way, because it's just a mismatch, right? And if you have smaller segments, usually, you know, it's not that 1,000 words or characters, it's smaller, like 300 to 200. Of course, with some small overlap, you can get much more higher differences, and this optimization works fine for searching. You can, for example, get top not one, not 5, just top 10, for example, of results. That's
yeah, and the other thing is that also when you are doing this similarity search, you don't actually need to rely only on the similarity score metric. There are some systems that are using alternative methods for ranking, not just like the most similar stuff, but doing a little bit more. Yes. Okay, I think the time
Yes,
is
I
up.
think that's it. I don't think we have time for any more questions. So a round of applause for Maciek.
Thank you.
So thank you, Maciej, for the talk. And now we're proceeding to the last part of the event today. We're running on limited time today. We need to leave the space by about 9:30. But before that happens, a couple of announcements first, and then we also have some lightning talks. So first announcement, the event doesn't end at 9:30. We're going to a nearby pub to continue discussion. I believe Maciej knows which pub we're going to. Where are we going to? Tea time. So we'll be going to tea time now. The question is, who's joining us in the tea time? Hands up. Okay, it's a bunch of people. Okay, so there will be a group forming probably around 9:30, and we'll go there. So that's announcement number one. The second part is that we're proceeding to the lightning talks now, and we do have one candidate for lightning talk already. Do we have anyone else who would like to talk about something in the next 5 minutes? Maciek would like to talk about something about 5 minutes. Anyone else? Indra, and we have a third lightning talk, so we have 3 lightning talks starting now. So Indra, would you like to start the lightning talks?
My name is Indra. I'm a developer and I'm import OpenAI in simple Telegram chatbot, and I'm interested in your feedback. Now I'm sending link on this Telegram chatbot in Discord. Yep. Maybe you can help me with this.
Coming. Okay, thank you. So you probably heard last Christmas song recently. That's because December is coming, and December also means one thing. But let me ask you a question. Do you like or love waking up at 6 a.m.? How many people love that? Raise your hand. Great, a lot of you. Do you love waking up before 6 a.m.? I do. Do you love coding puzzles? Who likes coding puzzles? Raise your hand. Yeah, probably a little bit more people. Great. Now you can do both. Because Advent of Code is starting. Advent of Code is an Advent calendar, which is starting in December. So every day at 6 a.m. There are new coding puzzles to solve, and there is a global leaderboard. I don't know, several hundred thousand of people are joining it at the same time around the world, and so do we at PyData Discord channel. Well, if you love both waking up before 6 a.m. and coding puzzles, that's great. It's for you. If you hate both, you can strengthen your character by facing both. If you only like one of those things, you will learn to love the other. That is my solution for this. But seriously, the waking up early part matters only if you want to participate in global leaderboard. So you want to sort of compete with other people who are complete aliens when it comes to speed of coding. Absolutely mental. But if you are not early bird, you can still do the tasks later, or even now you can do tasks from past year. And it's nice to have someone to discuss the solutions with. Yeah. So we have a channel specifically for that at PyData Discord, which you can join. I think Arthur was already saying this. It's discord.pydatakrk.pl, and the channel is named Advent of Code. You will see it. It has a little Christmas tree in there. And that's it from me. Thank you.
My name is Indra. I'm a developer and I'm import OpenAI to code simple Telegram chatbot. And you can see that now it's running. HTTP 200. Okay. And now I'm sent to Discord link on this chatbot. And now it's sending to Discord. 1 second. Yeah, its name of this chatbot is Somex, and it's AI that helps in personal branding. So it's funny AI. I use GPT 3 and 5 model now from OpenAI, and 1 second, I'm opening it. Yeah. And I'm now clear chat history. Yeah, and welcome to Somix AI revolution in personal branding and dating. It's AI dating, yeah. Personal branding advice, crypto investment tips, and AI boostment matchmaking. And now I push start and hope that internet will be okay. So it's reconnecting. You can see. 1 second, please. Yeah, and now we can see welcome to the world of Somix AI, where your name is the first step on a journey to new you. So, and now I'm test and I'm enter my name Indra Dev. Yeah. So, and now I have a question. It seems it's a loss for words. Maybe somebody can recommend how to work with data in Telegram chatbots. Yeah, and this feedback I'm looking for this Python community. So it's my question to audience. Okay, I understand. So maybe you can recommend with what libraries be best to work to correctly extract data for send this data to OpenAI API, and this API returns that these correct answers. Maybe someone expert in this field here.
But be careful, use the one before 2 weeks ago, because the one that they released on dev day, it has a lot of breaking changes. Or if you want even more abstraction and simpler stuff, you can try Langchain.
Can I little bit speak with you later? Thank you. So, and it's been my presentation, and I try to do more cool things with AI. Thank you, community, for all. Yeah.
Hi all, I'm Dharm, and I want to talk a little bit about RAG applications. So something that we saw in Maciek's presentation towards the end, how this vectorization and few-shot learning is used to extend capabilities in NLP and GPT-3. What exactly the diagram he showed is called retrieval augmented generation. So this is a big use case for many companies right now in terms of using GPT 3.5 or 4 or even generative AI further to basically create a question answering chatbot for a private data to your company that you don't want to give access to someone outside. You want to use it only internally. And based on that specific data, the bot is supposed to give you some answer. So what happens is the first step that everyone is understanding now is the biggest limitation is retrieval part. So the retrieval part is the part where given the question and given the vector of the question, you try to find the relevant context. So basically, let's say I have a book where I have 500 pages. So what I can do is I can create each page a separate vector, or what I can do, I can create smaller vectors like half pages only. And then based on my question, I will ask it, give me the 2 most similar half pages or 3 most similar half pages. So here is the first degree of accuracy. I think a lady there was asking the questions about RAG, and I guess maybe this could be helpful for her. So the what happens is this is a very prime introduction of error here. So your retrieval will be as good as your vectorization algorithm. So now there is one part that when you are building a RAG, either you use pre-trained model, which happens most often, or sometimes what you can do is put some effort and try to retrain the embeddings model, which is creating the vectors for you. And then the next step is the similarity matching, the similarity scoring. So like Maciek mentioned, there are very different metrics, a lot of various metrics that you can use to compare what kind of segments do you want to retrieve. So something is similarity matching, like you just compare the distances, and then a new metric that is being popularized recently is called maximum marginal relevance. So what it tries to do is it does not only try to match you the closest similar segments in numerical representation, it tries to give you a more diversified output. So let's say you tell it to give me 20 maximum, and then I want 5 outputs. So it will create brackets of 4 for each, and then in each bracket it will give you the maximum, the most relevant one, which ultimately increases the diversity of your retrieval. And then based on top of that, if you have a good enough context that you retrieved out and your decently formed enough question, then it's a piece of cake for GPT 3.5 or 4 model to actually answer your query. If your retrieval piece is not working, then no matter what you use GPT 3.5 or 4 or even GPT 5, which is upcoming hopefully in the future, it wouldn't solve your problem. So that's quite an important piece, and it's actually quite a very heavy ongoing research these days in terms of how to make vectorization work better and how to come up with better metrics for retrieval, scoring, and matching. Now I have a minute left, so I'd open it up for any questions.
Hello. So I'm also working on an RAG application, and one problem I come up with, which I think you also mentioned, was the fact that when you do like retrieval for some specific use case, like the usual similarity which is achieved via embedding models which are available publicly is usually not the semantic similarity which you are going for. And my question to you is, do you think that there is like the way out of this kind of situation that actually when you have very specific notion of what is similar to each other and what isn't, you actually are forced always to fine-tune your own model? And maybe kind of like guess of mine would be if it would be possible to train kind of in some self-supervised way embedding when you could give like a prompt with your notion of similarity you are aiming for such embedding model, so it could be more generalized.
I think that would be a little bit like going for the nuclear bomb to kill a mosquito. So I would think of rather a more simpler way out. First, I will go towards the use case. I will try to find out which kind of embedding gives me better results. Is it a token level embedding or is it a sentence embedding? And you need to be careful because the sentence embedding models don't they don't segment each sentence automatically from the chunks that you provided from the page. For them, one page or half a page or whatever size you define that this is my chunk, that whole is a sentence. So it's this play of words. So that's why one of the people mentioned here about changing the length of this context and figuring out what context length works better for information. So that's a very good advice. And on top of that, one more thing you can play with is that if your context length is getting much smaller, then you can ask your retriever piece to return more similar neighbors by default. Because I think, for example, in LangChain, I was using similarity and it was set at 4 nearest neighbors or 5. So you can play around, and if you have smaller chunks, you can be like, okay, give me 10 or 20. So that can help, and I think that's what these custom GPTs, which were released 2 weeks ago at Dev Day, are doing. So when you are able to create Q&A custom GPTs for your own use case on enterprise or premium accounts, there is a lot of mystery involved because it's a black box, and people have suspicions that they are using very, very large outputs, which is basically a high number of similar neighbors to give a large enough context that somehow your question will be answered. So it's just like saying, I asked the question from the book, and as the relevant context, I am giving it only 5 pages, or I'm giving it the whole book to answer the question. So that's how you can manage around by focusing first on the retrieval part, checking token embeddings or sentence embeddings. And then based on top of that, you can check some metrics like similarity score or maximum margin relevance.
I'm going to proceed to a final few announcements and then to a closing. Okay. And I'm gonna start with the same slide that Maciej finished at. That's the QR code and the website to get onto our Discord, so where we can continue discussions about all the topics that we mentioned today, and obviously play Advent of Code as well, but also continue the discussions. Just to repeat the announcement that Marcin made before, next week we have PyConic. If you go to pyconic.org, you will see all the details. There's another Python meetup in town that's happening next week. Also on meetup.com, where you can sign up for the event. Another announcement. So we do need to clean the space in about like 3 to 5 minutes. So as soon as I finish, we need to slowly start going. There will be a group forming to go to the after party. I think Maciej will lead us, everyone there. Everyone knows Maciej, so yeah. So one more announcement. There's another event. It's in Prague, not in Kraków. It's in February, but the call for proposals opened this week. So Python Pizza is a different type of event. It's a full day event, but the talks are all 10 minutes each, and there's a pizza in the middle. There is the keynotes were announced. The venue was announced. If you go to prague.python.pizza, I'm not sure if you can see the URL at the top. But if you go prague.python.pizza, you will see all the details. The call for proposals is open. And if you want to learn more about PyData Kraków, you can go to our website. All the links are there. They're a bit small, so you can probably see them on the slides. But yeah, if you want to submit a talk, if you want to speak at one of the future events, if you want to sponsor one of the future events, or if you want to join us on Discord or LinkedIn or anything like that, all the details are on the website. And I think that's it for today. Let's a round of applause for our speakers today. And another round of applause for Zendesk, our amazing host and sponsor of the meetup. And thank all of you for coming, and see you on the next meetup, either on PyData or PyConic or any other one in town. And thank you very much, and see you next time.